Okay. This week we will wrap up all the courses, and the last topic that we are covering is the Z-transform. We have been seeing a lot of Z-transform examples. We will continue seeing Z-transform examples, and we will make a list of the properties for solving questions, which will greatly help us in determining the Z-transform and the inverse Z-transform, of course. Now, the next topic, or today's topic that I want to talk about, start with, is the geometric system response evaluation. Did this for the Laplace transform, and we said that for the Laplace transform, if we have poles and zeros, we have this kind of a situation. The difference or the distance between the j omega axis point and the zeros will be in the numerator, and the distance of that point to the poles will be in the denominator, and they will be multiplied, and that in general will give us the frequency response magnitude if you are only considering the distances. If you are considering the angles will correspond to the phase of the frequency response or the system response. What do we mean by the system response? The system response is h of e to the j omega, or h of z in general, but z is equal to e to the j omega, or the unit circle for this case will be the system response. For the Laplace transform, it was capital H of j omega, of course. And it has two parts. One part is the magnitude, which is the critical part for us. We will mostly deal with this one. And there's, of course, the angle of h of e to the j omega 2. So how are we going to find these magnitudes and angles from the geometric representation of the poles and the zeros? We will start, let's do it over an example. Actually, it's the same here. We will look at the distance of j omega to poles and zeros. Okay, we will do the same. But the distance to the j omega is not now the j omega axis anymore. You may remember that the situation for the Laplace transform was the j omega axis, but now we are interested. It was an axis. This is an axis. This e to the j omega is a circle. For each omega value, you will be on the e to the j omega circle. Let's think of an example. H of z, let's say, is equal to 1 over 1 minus a z inverse, which is the first example that we solved. And let's assume that z is gray is the response. Let's also say that magnitude of A is less than 1. So the unit circle is included in the region of convergence. As a matter of fact, this is the necessary condition for the system response if it is not in the region. Then z will be that omega. This probably you started not hearing me anymore, so I will rewind and repeat those things. But first, let me see which wireless I should connect to. So excuse me about that. I may want to get left out, and then I will connect again. I hope now you can hear me back. Sorry for the interruption. So what I was really saying is that you have an h of z, like this example, where it may correspond to our first examples. And if the unit circle, if z is equal to e to the j omega, is included in the region of convergence like this, then you can say that h of e to the j omega is equal to h of z at z is equal to e to the j omega. Now, the problem here is it's very difficult to find the magnitude, for instance, from here. But you can do that. If you are good at mathematics, you can say that it's equal to the square root of h of e to the j omega times h conjugate of e to the j omega. Okay, so you take the conjugate of the expression and multiply with this expression and try to obtain something real and then take the square root of it, etc. That would be a little bit difficult. It's actually more than difficult. It's very difficult. But you can do that. It's still manageable. You can, for example, see that when omega is small, like omega is equal to 0, let's say, then e to the j minus j omega will become 1, and 1 over 1 minus a, if a is positive and less than 1, it will reach to its maximum. So it has a peak at omega is equal to 0. And it also reaches to the peak when omega is equal to 2 pi. But when omega is equal to pi, e to the minus j pi is equal to minus 1. So the overall expression will be 1 over 1 plus a, which is the smallest value. So at pi or minus pi or 3 pi, odd multiples of pi, it will reach low, and at 0 or 2 pi, it will reach back to a high value. At 5 pi, it will go back to a low. At 6 pi, it will come back to a high value. So I can inspect that the situation is a little bit low pass, but there is a better way to reach to that conclusion, and that is exactly the same way we did for the Laplace transform. We draw the poles and the zeros. There is 1 0, by the way, and 1 pole, because this is equal to z over z minus a, as we already know. So at z is equal to 0, we have a 0. And at z is equal to a, we have a pole. Let's say it's here. Now let us draw a unit circle from 1. Okay. This is 1, this is a, and this is 0. Now the overall magnitude response is equal to the distances from zeros multiplied divided by the distances from the poles to the unit circle. So we choose a point, let's say this point on the unit circle, and we take a look at the distance from the pole, which is this one, this distance. It's d1, let's say. And this distance from the 0 is n1. It's in the numerator, and d1 is in the denominator. Therefore, we say that the magnitude of h is equal to n1 over d1, because there is 1 0 and 1 pole. If there are multiples of poles and zeros, it will be n1 times, n2 times, n3 times, n4 times, etc., over d1 times, d2 times, d3 times, etc. But we have 1 pole and 1 0 here, so it's n1 over d1. By the way, what is omega? Which frequency are we talking about? Let us zoom to that and indicate it in a better emphasis here. This is the frequency omega. From the real axis, the angle that it makes. When omega reaches to pi, for instance, it becomes purely imaginary on the axis, imaginary axis, and it is the highest, sorry, it's pi over 2, excuse me, it's pi over 2, it shows, it starts showing some oscillations. When it reaches back to pi, that is the highest frequency. And after pi, it rolls back all the way back to 2 pi. And 2 pi is exactly the same as omega is equal to 0. Because when you make one loop, you come back to the 0 angle. Okay, that's why h of e to the j omega is 2 pi periodic here. Now let's make it again smaller. So that is the omega. And at that omega value, the magnitude of h of e to the j omega is equal to, therefore, n1 over d1, as we said. This is the real axis. This is the imaginary axis. Now we can make a few observations from this one too. First of all, this example, n1 always equal. Again, am I connected? No, I'm not. I think there is some communication. Is equal to pole is in the sorry, the 0 center. Therefore, the units of the say that of h of e to the j omega is equal to 1 over d1. And we can, I can see from the figure that as omega becomes smaller, or around 2 pi or around 4 pi, which corresponds to the same 0 frequencies or small frequencies, this distance d1 becomes the smallest, okay, because you come near to the pole. And then if you increase the frequency, for example, if you come to here, this frequency, then the distance from the pole will be larger and larger. Whereas the distance from the 0 will always be equal to 1. So I'm becoming distant from the pole. And when I reach 2 pi, when I reach this point, the distance from the pole will be the maximum. So 1 over that maximum distance will become the minimum, which gives me an impression that I have this kind of a situation on the magnitude of h of e to the j omega plot on the frequency axis. Around small frequencies, it reaches to a large value, and then it becomes smaller and then reaches back to a large value, and then it continues. Okay, getting low and high and low and high again. This is where pi is. This is where 2 pi is. Now, clearly, if A is like this, somewhere between 0 and 1, this is what we will have. But let's make A closer to 1. If it is closer to 1, then the situation will be more like this. So at 0 frequencies, the distance from A to 1 will be smaller, so it will be a smaller thing in the denominator. Therefore, h of e to the j omega magnitude will be even larger. And similarly, since A is closer to 1, its distance to the -1 crossing point will be larger. Therefore, 1 over that larger number will correspond to a smaller value here. So this will be smaller for the blue case, and this will be larger for the blue case. This is A is closer to 1 case. If you exactly come to A is equal to 1 case, if you just put or locate the pole on the unit circle, then clearly this will blow up to infinity. Okay, it will go diverge to infinity over there, because 1 over 0, the distance will be precisely 0. 1 over 0 will be infinity. The angle, on the other hand, let's also talk about that one, although I'm not very much interested in those things for the time being, but you have to know it. So we write it like h of e to the j omega in magnitude, it's equal to the magnitude of v1, which is the distance to the 0, divided by the distance vector to the pole, and the angle of h of e to the j omega will be equal to the angle of v1 vector minus the angle of v2 vector. So we have to measure the angles. The angle from the original 0, from the central 0, is the same as omega. It's a good expression, but the angle to v2 is a little bit more complicated, and I can see that it's increasing quite quickly. For example, at this point, the angle of both of them are 0, but as I move to here, the angle of the pole increases more than omega, which is the angle of the 0. So you just have to plot those things. Now, if you have more than one pole, more than 1 0, etc., you have to take a look at the distances, the corresponding distances, and you have to say that magnitude of h will be equal to n1 times, n2 times, n3 times, etc., divided by d1 times, d2 times, d3 times, etc. Now, at this point, the critical thing, before coming to the critical thing, let me talk a little bit about the situation of the surface on the z-plane. The surface on the z-plane. The z-plane, you can think of it like this. I will try to plot it a little bit surface-wise, three-dimensional. This is the real axis, this is the imaginary axis, and this is the magnitude of h of z, okay? This, at this point, at the locations where there's a pole, they will look like surfaces that go up to infinity, like this, okay? Maybe I should consult to readily available stock images from the internet. So this is a circular situation where this peak value at this point and this value at this point, they correspond to poles. Okay, we have poles here. At the positions of the poles, the magnitude of h of z goes up to infinity. And what we are really doing on the Laplace transform case is to think of this three-dimensional surface as a profile, and we are cutting from the j omega, the imaginary axis, if you may remember. We talked about this before. Now, on the contrary, so it's like a cake, and the cake surface makes a surface, and we are cutting the cake from the j omega axis, which gives you magnitude of h of j omega. But for magnitude of h of e to the j omega, for the discrete time case, it's the same cake, kind of, but we cut circularly, okay, and take a look at the profile, the two-dimensional extension of the circular cut of the cake. We fold it open from minus pi to pi. We take a look at what the cut surface really looks like. That is the Z transform. And for that, I want to show you something. And for that, I will stop sharing from my tablet, and I will start sharing from my laptop. So I'm now sharing my laptop. Can you see my laptop, by the way? Are you able to see what I am seeing? For example, I want to show this figure. In this figure, as I say, there are, it's similar to the figure that I tried to draw. There are essentially two poles, and this red circle essentially corresponds to the unit circle, and on that unit circle it shows some inclinations and declinations, so it has a value. It's a three-dimensional profile, and in this profile, as you come nearer to the pole, as you see, the value increases and then it decreases back at pi. So it's a bandpass. This thing looks like a bandpass filter, by the way, right? Here I can see that there seems to be a zero somewhere here because it touches to the around pi over 2, it reaches to a maximum. Around pi, it goes back to a small value. Around minus 3 pi, it reaches back to a high value and comes back to a low value at back to 2 pi. So we make a rotation. Now, many of the applications tend to plot only from 0 to pi, because from 0 to pi, it is symmetric to, in terms of magnitude, it is symmetric to what we have from 0 to minus pi. So from minus pi to pi, it will be two peaks. And when you cut from 0 and look at only towards pi, that's the technically or engineering-wise better way of looking at it. It just shows you a single peak like this one. Okay. Another figure I can see here, as you see, there are two poles, and those poles exhibit some large values, and the magnitude frequency response is the blue profile, where we cut this three-dimensional shape and fold from minus pi to pi or from 0 to pi. Now, I want to show you something else. I found this yesterday from the internet. It's called PZ tool. On the internet, you may search for it by these names. PZ underscore geom underscore s. It shows you the geometry on the Laplace plane. This is PZ tool, which I will show you what it is really doing. Applications, standalone Python applications, I guess, which you can run. Now, what is it doing? Here, this is a system with a single pole and two zeros. And as you see, the zero is at a low frequency. Therefore, the distance from this zero to the unit circle, the gray circle is the unit circle. The distance here to the zero will be very small. So in the denominator, there will be a very small value at that frequency angle. Therefore, at that low frequency, as you can see from here, it reaches to a small value. And as the frequency to pi, which is the highest frequency, the right hand side equation, the distance from the zeros will be larger. By the way, there's only one pole in the center at z is equal to 0. The distances from the zeros will be more, and magnitude of h of j omega will, as you see from here, they tend to increase. This is a very nice application, by the way, where you can add and remove zeros and poles. Let's add a reciprocal pair of poles. Now, for example, I add some poles at this frequency. That's a bad one. Let's make it more like this. And then I add another pair of poles, which is, let's say, somewhere here. Now, what do we see? What is the observation that we make here? Because of this zero, the conjugate pairs of zeros, it touches this frequency that I'm marking with the cursor. Please take a close look at that cursor. And then at a certain frequency, the distance from the pole is becoming smaller at that frequency. Therefore, it shows a peak. And then it goes down a little bit and then reaches to another peak, which is this time the distance because of this pole that we have. Let us add a few more poles. For example, maybe by the way, the mouse of my laptop is just broken. Just does not work. Anyway, yeah. I am trying to make a nice bandpass filter here. So around the frequencies corresponding to these angle slots, it is passing more because you are getting nearer to the three poles that we have. But in order to make it even look better, let me add some zeros at near to here. So it reaches down to 0. So it becomes like a bandpass now. From 0 to pi, it reaches to a high value and comes back to another low value, which is low pass filter. Now, this application that I found on the internet, I want you to find PZ tools, pole zero tools, sort of. You can also find similar toolboxes for the Laplace transfer function magnitude as well. It also shows you the magnitude in decibels. It's capable of doing it like that. And it also shows you the phase as well. It's nice, but of course we are dealing with the magnitude for the time being. I want you to find it and explore it and make a lot of explorations. Make sure that you're capable of drawing or obtaining low pass, high pass, band pass, band reject, double band pass, double band reject filters with a lot of poles and zeros, of course. You just need to locate them at their proper locations and see what they really look like. Why am I telling you this? Because in your examinations, there will be multiple choice test questions, which I will just give you a pole zero plot, and I will give you 5 candidates of h of e to the j omega magnitude plots. So the left-hand side plot will be given, and 5 candidates of the right-hand side plots will be given to you. And you have to find the correct one, which magnitude corresponds to which pole zero pattern. You have to match them properly. Or vice versa, I may give you the magnitude response and which pole zero pattern is the correct pole zero pattern that will generate it. That could also be a question, but not one question. Of course, I will ask you 5, 6, 7, maybe 10 questions from here, all very easy test questions. You will have to closely inspect and see what kind of a situation it produces. Of course, you're not allowed to use the PZ tool or any tool that you can find, or MATLAB if you have, during the examination. You have to make the inspection visually, but the answers will be very obvious. Look at this. When I look at this pole zero plot, I can immediately see that it's a bandpass filter. Between this frequency and this frequency, it shows a small distance to the pole, so it shows a large value, exhibits a large value, and around low frequencies and around frequencies of pi, which are high frequencies, it must be suppressed. It must be high in the middle with some ripples, maybe 3 ripples I would expect, because there are 3 poles. So these are the ripples: the first ripple, the second ripple, and the third ripple. These are the ripples. So this must be the answer: visual inspection. Okay. So you will have these as the test questions. Now I want to stop sharing. How can I do that? How do I stop video sharing? Maybe from here. Yeah, here. That is it. I stopped the sharing. Let me go back to Zoom. And let me start sharing from here again. Okay, I hope it's clear the way that we do the magnitude response evaluation is clear, because you will have a lot of questions from there, as I said. Now, without losing any further time, I will start explaining the listing out the properties of the Z transform. Some of these properties will be extremely useful. Some of them are very obvious. The first one is the obvious one. if you have this kind of a combination of discrete time signals, then the corresponding Z transform will also be combined with the same coefficients, A times x1 of Z plus B times x2 of Z. This is the linearity. Now, although it's obvious, the thing that you have to be careful about the region of is the region of convergence. So the region of convergence, we say, includes R1 intersection R2. Again, there may be some pole zero cancellations. So out of a circle, inside of a circle, they may a little bit change. But if there is no pole zero cancellation, then the region of convergence is just the intersection of region of convergences of x1 and x2, naturally. The second one is time shift, x of n minus n0. The Z transform of this one is Z to the minus n0 times x of Z. And again, it's quite obvious because we know that in the Fourier transform case, it was e to the minus j omega n0 times x of e to the j omega. Okay. Since e to the j omega is Z, this expression could be written as Z to the minus n0. How about the region of convergence? The region of convergence does not change actually. It stays the same. But you can say that we have some additional poles. If n0 is positive, then z to the minus n0 is like 1 over z squared if n0 is 2, for example. Or if n0 is 1, it will be 1 over z. And 1 over z makes a pole at z. 1 over z squared makes 2 poles at z is equal to 0, right? 1 over z cubed makes 3 poles at z is equal to 0. But they're all at z is equal to 0. And remember what I said, z is equal to 0 is not in the z plane. So in the finite z plane, we don't contribute any further poles. You may contribute poles or zeros at z is equal to 0, but finite z plane is not affected. Okay, so the region of convergence technically does not change. We just incorporate some poles or zeros at z is equal to 0, which is fine. The third property is scaling in z domain. It's like at the right-hand side of the z transform expression, the z transform expression, in other words, is capital X of z over z0. So I'm scaling in the z domain. What does it correspond to in the X of n domain, the time domain? This essentially corresponds to, it may correspond to several things. For example, if z0 is, let's say, -1, okay, that's an interesting situation, by the way. When z0 is equal to -1, it really corresponds to z0 is equal to -1 is equal to e to the j pi, because e to the j pi is -1, as we know. Then z over z0, which is z over -1, or z times -1, it doesn't really matter in that aspect, is equal to e to the j omega over e to the j pi, which is e to the j omega minus pi. Now that's interesting, because if it means there is a shift, there's some amount of shift in the frequency. And we know that if you shift in the frequency, then you have to multiply with a sinusoid in the time domain. And that sinusoid for this overall expression appears to be like this: x of n times z0 to the power n. Where z0 could be just complex. It may have real parts, it may have imaginary parts, it may be a complex exponential, then the magnitude is 1, but its magnitude may be different as well, z0. It may be totally real, like 2 to the power n, okay? Then the right-hand side part, which is the z transform, will be capital X of z over 2. So this is the overall expression, and the region of convergence essentially changes according to the magnitude of z0 times r. What I really mean is, for example, let's assume that there is a pole which determines the boundary of the circle. That circle's pole position is multiplied by magnitude of z0. For instance, if z0 is 2, and let's say that the circle out of a circle was at a is equal to 0.6. Okay, so it's out of the circle with a radius of 0.6. Now the pole will be moved to 2 times 0.6, to another 1.1 position of radius, a pole radius. Let's say radius is more 0. And is on like one, as you said, it doesn't actually is. There seems to be further problems, but I don't know why it's just doing this. To be, I was just doing this. Okay, I think it may be a good idea to think. It may be a good idea to stop at this point. I will try to fix out all the interconnections, and afterwards, after fixing my connection from my tablet, we will continue. We were left at some concepts, and we will continue from there. Okay. So let me stop the recording at this point. What time is it? It is 9:42. Let's meet at 10 o'clock. Okay, at 10 o'clock we will meet again. Until then, let's give some break.